So what we'll be talking about is granular media filtration, and we'll look at the practical applications of granular media filtration along with issues related to the operation and maintenance of these filters. Now, in this figure here, what's plotted is the turbidity here versus filter runtime and head loss versus filter runtime. This bottom line here is for an approach velocity of 2 gallons per minute per foot squared. So that's foot square of surface area. Okay. This bottom here corresponds to the turbidity of that same water. So it's the turbidity in the effluent. The yellow is the head loss for the filter effluent at 5 gallons per minute per square foot, so increased by a factor of 2.5. And this is the effluent turbidity. So what has happened here? Okay. Things are going along really, really well. It's got a low turbidity, some fluctuations here. The head loss is pretty constant. And then all of a sudden, we see this significant increase in the turbidity. So what can be happening here? Why could this have occurred? Number of factors. One, perhaps there was a storm event. There's a slug of higher turbidity water moving through the system. The operator didn't notice that, so didn't increase perhaps the coagulant dose, or perhaps added either too much or too little chemical dose. But there was some sort of malfunction previously that would have resulted in this increased turbidity. And you can see, not surprisingly, at the higher approach velocity, the impact of that failure is much greater than at a lower approach velocity. Now, this is for a sand filter. As I mentioned, we have single media, and then dual media are the most common types. One of the reasons we use dual media is it's much less susceptible to upsets. It's much more likely that you're going to have this type of a condition in a single media filter. So somebody mentioned bigger particles, okay? Perhaps, okay, bigger particles probably would have gotten stuck on the filter, on the top of the filter. They might have been removed by sieving. But there are particles definitely moving through the filter. Now, typically, in terms of deciding which of these types, whether to use single or dual media filter, typically, if you're looking at treating groundwater, you can use any of the types. Generally, with a groundwater system, especially if you've got multiple wells, you can blend the water from these wells in order to achieve a relatively constant hardness, which, if that's what you're removing, into the system. So your water quality is managed by adjusting your flow rate from your wells. You've got some control. Problem with surface water is you have very, very little control. Water quality can change rapidly, and it changes seasonally. So because of that, with a surface water system, you typically do not want to use a single media system. You'll use dual or multimedia. If the water quality changes slowly, So for instance, this could be a deep intake in a lake, in a large lake. So for instance, the intake for Great Lakes Water Authority's Port Huron plant, Fort Gratiot plant, is out in Lake Huron. It's very deep, and the water quality is relatively constant. So there they could probably get away with a single media filter. On the other hand, if you're treating, Ann Arbor uses a combination of groundwater and and the Huron River water. The Huron River water is going to change. Water quality will fluctuate rapidly with storm events. It'll change with changing temperature. So a dual or a multimedia system makes more sense there. When we design these filter systems, you will always use an even number of cells. And I'm just going to skip to this. This is a photo from the Lansing Dye water treatment plant. The water flows down the center below the floor level. You then have water flowing to each of the filter banks here. So each one of these here corresponds to a filter bed. Because of the complexity of your pumping system, you will always have an even number of filters. So they're always designed in this way, with the main pump down the center and then your filter beds off to either side. So you'll always have an even number of filters. Smaller plants, you need a minimum of 2. Remember, you need to be able to operate the entire plant, with 1 filter out of service, 1 unit out of service. So you want to be able to ensure that you can operate the system. So when you're designing this, you'll have multiple filter beds, but always an even number. Larger plants, you want a minimum of 4, and you can use this equation to determine the number of filters. Your filtration rate must be designed for 1 filter out of service. If your flow rate is too high through the remaining filters, then you can get particle detachment. Remember, I said you need both particle attachment and particle and you want to minimize particle detachment in order to obtain good quality water. So you've always got those 2 phenomena working against one another. You want to minimize that particle detachment. If your flow velocity is too high, then you get poor water quality. And you need to remember that in your design. When in the East Lansing wastewater treatment plant, when they designed those filters, the engineers forgot to consider this. And when they have a high flow, so storm event, and they're backwashing a filter, they have to bypass some of the water around the filter because they can't treat it all, because somebody forgot to do this set of calculations. Don't be that engineer. The dimensions of these can be anywhere from 25 to 100 square meters. It can be up to 200 square meters, but typically under 100. When you're designing these, this is a filter bed, the whole thing. Either side is your filter cell. So we have 2 filter cells, the gullet down the middle, and the two together make up a filter bed. So when we say even number, I mean even number of filter beds. This center is the gullet. These are the wash troughs. These are concrete. They can also be metal wash troughs. This is one cell. This is the other cell. Together, this is your filter bed. It's just a cutaway of the same thing. You can see here's your gullet. You've got the wash troughs here. You have your collection system with all the laterals at the bottom. You have a gravel support. And then you have your sand on top of that, and then the water level. This is a photo of the filter during normal operation. So the water level is high. It's above the top of your water troughs, and the water is flowing down in this situation. As I mentioned, when backwashing, when the head loss is too great or the turbidity exceeds a set limit, or you reach a maximum time limit is 3 to 4 days. In some cases, it's backwashing is much more regular than that. And so when that happens, the system is backwashed. This can be done with water only. It can be done with a surface wash. It can be done with air scouring. As I mentioned, air scouring is often used with surface waters where you have the clay, the silt particles forming these essentially what we call mud balls. So just kind of think about when you were a kid, you were playing in the mud, how the clay tends to aggregate together. It used to be that the backwash water from a surface water plant could be sent back to the headworks of the plant, but that's no longer the case. This is a photo from the dye plant. This is during backwashing. So the water is flowing upward through the filter bed, so it's fluidizing the bed, and that water is flowing over the sides into the top of the wash trough and into the wash trough, and then to the gullet. And then in this case, this is a groundwater plant. Because it's a groundwater plant, they are able to recycle this water to the headworks of the plant in order to capture that calcium carbonate precipitate again. So it basically goes through the whole plant all over again, try and capture it a second or third time, and also to use the excess calcium hydroxide in there to help raise the pH. So it helps reduce the dosage of lime that they need to add. So in this situation, because it's a groundwater plant, they're able to do that. This is another photo from the operation.